case you need reminding, let's see here, what is due today? Your homework number 2, aka the calculator project number 1, is due today. And by Friday, the 22nd, at our review session, the homework number 3 test review is due, which obviously means that on Monday we're going to have our first test. So I guess I need to start making that sucker up. But so this is my plans for today. Today I'm moving on into chapter 7.1. And then on Friday's class, I'm going to keep on going and double into chapter 7.2. And then, what little we get into that. And then at the review session, I'll go over the entire review packet. I do plan on recording the session, God willing, and the computer systems work and stuff. I'll record that session. Obviously, you'll have all weekend to study for it. This is a great review for the homework set. And I'll also post a link to the video that I make up here to give you guys something or other. Your test is on Monday. So I've got Joseph in the back collecting these calculator projects right now, and so go turn those into him. And we're going to go ahead and get started on what we left off with. All right. We just started and introduced the idea last time of area between two curves. And so when I was looking, basically talking to you guys about the ideas, there's 2 formulas that you're going to basically need to know for this particular section. And these forms are going to come back and haunt you again when you get you guys into Calculus 3 when we start doing this multivariable stuff. The formulas are very simply this. You've got, anytime you've got a function, you got to basically graph a function. You got a function on top, a function on the bottom. You've got your points of intersection by setting to 2 points equal to each other. And to find the area between 2 curves, it is the integral of the top function minus the bottom function, dx, from A to B, from your points of intersection. Or, if you happen to graph a region and it happens to be not a function, you've got a curve on its side, clearly vertical line test, it violates. But if you look at the region, you have a distinct right side of the region and a left side of the region. Then it's the integral from C to D, your points of intersection in terms of y, integral from C to D of f of y minus g of y dy, right minus left dy. So, simple terms, it's top minus bottom dx, right minus left dy. That's what I'm after. And you got to pay attention to this stuff because the way you orient your region is really going to have to depend on whether you have to do a lot of work or maybe just a little bit of work. So there's a pattern to this stuff. So, and last time we did the algebra review session, and that's basically solving for one variable in terms of the other, vice versa. So this one, you have the function in terms of y. We want to be able to solve for y in terms of x. This function is in terms of x, and I ask you guys to solve for x in terms of y. So, let's actually do a problem. So here's what we picked up last time. And here's my formula, integral of from A to B of top minus bottom dx there. And we got an equation here. It says this. Sketch and find the area bounded by the curves f of x equals the square root of x and g of x is equal to x divided by 3. Well, the first thing I'm going to do is get an idea of the graph of this guy. And you can put this on the calculator if you don't know what the graph looks like, but you really should. The square root of x starts at the origin and bows out. So here is f of x is equal to the square root of x. G of x, same thing as y, is x divided by 3, 1/3 x. So 1/3 x, I have a slope of 1/3, so it's a line. So it comes in like this and hits the point and then moves on. So this is g of x, which is equal to x divided by 3. So we're talking about the region captured between the curves. Now this is the important part here, is I've got to identify the region. And region captured between these 2 curves, we're talking about this region in here. And as you look at this region, I clearly see I have a top part of my equation and a bottom part of my equation. But the other thing that I need is I got to have the points of intersection. So to find the points of intersection, you're going to set the equations equal to each other. So the square root of x is equal to x divided by 3. Now what kills off a square? root, excuse me. What kills off a square root? Square. So I'm going to square both sides. This square and square root cancels. I'm left with x is equal to, and powers distribute through strict multiplication division. This would be x is equal to x squared divided by 3 squared, which is 9. I'm going to multiply by 9 on both sides to get rid of my fractions. This gives me 9x is equal to x squared. And because it's a quadratic, I'm going to set it equal to 0. So I'm going to subtract 9x from both sides. So I get 0 is equal to x squared minus 9x. And you clearly see you have an x in common, so I can factor that out. It'll be x times x minus 9. I set each factor, x equals 0 and x minus 9 equals 0. And I solve for x, so I get x equals 0 and x equals 9. So my points of intersection are actually 0 and 9. So there's some algebra to be had to show your work on this stuff. So I have my points of intersection between 0 and 9. So to find the area, it is the integral from a, which is 0, to b, which is 9, of your top function. The function on top is the square root of x, minus the function on the bottom is x divided by 3 dx. Top minus bottom. So now, I'm going to integrate the guy, but I don't do square roots. So area is equal to the integral from 0 to 9 of x to the 1/2 minus 1/3 x dx, just cleaning them up. So when I integrate x to the 1/2, add 1 over add 1, that'll be x to the 3/2 over 3/2 minus 1/3 is a constant, leave it alone. Integral x is x squared over 2. No plus c's on this thing because you got balance from 0 to 9. I'm going to clean this guy up. When I divide by a fraction, I invert multiply. So this is 2/3 x to the 3/2 minus x squared divided by 3 times 2 is 6, evaluated from 0 to 9. And then according to the fundamental theorem of calculus, you plug in top minus plug in bottom. So this is 2/3 9 to the 3/2 minus 9 squared divided by 6 minus plugging in bottom, but plugging in 0 is pretty nice. You pretty much get 0. So now, assume this was on a no calculator section of the old exam there. What is 9 to the 3/2 power? Remember, 3/2, your numerator is your power, your denominator is your radical, so it's half, 3/2. That's a square root of 9. Square root of 9 is 3. Cubed is 27. Divided by 3 is back to 9. Times 2 is 18. Minus 9 squared is 81 divided by 6. And so when you put this on your calculator or get your common denominator, it's equal to 9/2 or 4.5. But here's the deal, and this is that physics application stuff. What did I ask you in this particular problem? I asked you to find the area. Since I mentioned the word area, just don't set up an integral. I just asked you to find the area. This area, and you must denote it as area. Now, when you talk about units being feet, meters, whatever system you're working in here, straight line units is distance. Meters, feet, inches, centimeters, whatever. Squared units is area, and cubic units is volume. Because we're talking about area, I would like to see on a word problem, units squared. And there's my answer. Now on WebWork, you just type in the number, of course, but when you're talking about a word problem, I expect to see some units in this section. So the first section is when you're talking about area, I want to see units squared, and later on when we talk about volume, I want to see units cubed. Now if I gave you the units, this thing was measured in inches, then yeah, it'd be great, inches squared or whatever, but typically I won't give you the units, just say units squared for area. All right. So take a look at this guy. And that other formula I was telling you about, if your function is in terms of y, well then you want to do right minus left dy. So the big deal on this one is curve sketching. What does x equal y squared look like? Now we know that y equals x squared is a parabola facing upward. X equals y squared is a parabola on its side. And because it's a positive y squared, it is opened to the right. This is what x equals y squared looks like. Here, since I solved this function in terms of x, I'm going to solve for this one. I'm going to solve for this one for x in terms of y. This is a function x equals y squared, so this is in terms of y. This is x minus 2y equals 3, so x would be equal to, adding 2y to both sides, 2y plus 3. But you should recognize this, because the power on the x is a 1, the power on the y is a 1. This is a line. So where is this line going to be located at? Well, personally, I just start plugging in some numbers and try to figure it out. If I plug in y is 0, so on your y-axis, here's y is 0, your x-coordinate is going to be 3. 1, 2, 3, somewhere right there. Okay? And if I happen to plug in x is 0, here's your y-axis here, x is 0. When x is 0, I would solve for y, subtract 3 and divide by 2. That would give you a negative 3/2, and that's right there. So, and it's a line, so all I needed was 2 points. And I connect my dots. And this is what my line looks like. So we're talking about something, honestly, quite simple when it comes to lines. But most people, you're familiar with the y equals mx plus b. You plot the y-intercept and then you do the slope. That's great when you got y equals. But when you have x equals, my suggestion is when you got a power of 1 on the x and a power of 1 on the y, something of this fashion right here, and you had to solve for x in terms of y, x equals 2y plus 3, you know it's a line, just plot a couple of points. And the easiest points to plot is plugging in y is 0 and figure out the x-coordinate, and then plug in x is 0, plug in the y-coordinate, you got 2 dots, and the line's going to connect to 2 dots. But now, so this is all about identifying the region. This is the region we're talking about here. And you can clearly see I do not have a distinct top-bottom because of the parabola. The top and the bottom are the same thing here. This is not a function. But what you should really see is I have, of my region, I have a distinct right side, right equation of my region, and a distinct equation defining the left side of my region. So I've got to find the points of intersection. So to find the points of intersection, what do I have to do? I got to set the two equations equal to each other. My two equations are x equals y squared and x equals 2y plus 3. When I set them equal to each other, I get y squared is equal to 2y plus 3. Once again, it is a quadratic, so I'm going to set it equal to 0 and solve. So I'm going to subtract 2y from both sides, and I'm going to subtract 3 from both sides. That gives me y squared minus 2y minus 3 equals 0. And you'll notice that this factors nicely. Y squared minus 2y minus 3 factors into y minus 3 times y plus 1. Set each factor, y minus 3 equals 0 and y plus 1 equals 0, and solve. I get y equals 3 and y equals negative 1. These are my points of intersection. And you notice they're y-coordinates. So it's y equals, and there's negative 1 right here. That's where it meets up at. And this point up here is y equals 3. These are my y-coordinates of my points of intersection. So, to calculate the area is equal to the integral of right minus left when I'm doing dy's. My right function is the line, which is the 2y plus 3, minus the left function is the parabola, which is y squared. dy, and these have to be y numbers since I'm doing dy, and your lower on the bottom bound is negative 1 to the upper 1, 3. So this is the integral that sets up the area between these two curves. Now, I'm going to clean it up. So this turns into, and with a negative, you would distribute, if you had more than one term there, this integral from negative 1 to 3 of 2y plus 3 minus y squared dy. Integrate 2y with respect to y is going to be y squared. Integral of 3 with respect to y is 3y. Minus integral of y squared with respect to y is y cubed over 3. Evaluated from negative 1 to 3. According to the fundamental theorems, you plug in top minus plug in bottom. This would be 3 squared plus 3 times 3 minus 3 cubed divided by 3 minus negative 1 squared plus 3 times negative 1 minus negative 1 cubed divided by 3. Crunching it out, 3 squared is 9, plus 3 times 3 is 9, minus 3 cubed is actually 27, divided by 3 is 9, minus negative 1 squared is 1, 3 times negative 1 is minus 3, negative 1 cubed is negative 1, negative that makes it plus 1/3. So yay, we got fractions. So these two 9s cancel, so I'm left with 9 minus, and over here, negative 1 minus 3 is negative 2 plus 1/3. So this is 9 minus negative 2 is the same thing as negative 6/3 plus 1/3 is negative 5/3. And minus a minus a plus, so it'll be 9 plus 5/3. 9 is equal to what? 27/3 plus 5/3 is 32/3 watt. Very good. It's area, so I want to see that units squared. And I want to show you guys that, yes, you can do fractions without a calculator. It's not that difficult. Does that make sense? I'm setting you guys up for what I anticipate them doing. This will be the worst kind of problem they do on the no calculator part of the final exam or something like that, just to let you know. Okay, so how bad can they make it? Well, let's take a look. It says, sketch and find the area bounded between the curves f of x equals 4 sine of x and h of x equals 4 cosine of x on the interval between 0 and pi. So, they've given me bounds, 0 to pi. So, and I try to help you guys out with this thing and draw out my graphs here. Here is 0, and pi is right here. So, this is where I'm stopping. This 0 is where I'm starting at. So I'm only focused on between these two guys. Now you should recognize your graph. Now, the 4 sine of x graph. Well, sine of x is a wave. You expect that. It's a classic sine wave. But sine waves always starts at the origin. So this is starting at 0 up here. This is the equation of y equals 4 sine of x. Cosine, 4 cosine of x, always starts at the amplitude when you plug in 0. So this equation right here is the equation of y equals 4 cosine of x. Identify area graphs. But now, here's the important part that tends to frustrate a lot of students. You got to look at this thing and see what is the area captured between these two curves. Starting at 0, here's the area, here's the cosine function, and here's the sine function right here. But at this point, they switch. This went from being on top, now it's on the bottom, and this is on bottom to top. So this is still area captured between these two curves. And again, we're stopping at pi. So we're talking about two different regions here. Because what happens is your top switched over to the bottom and the bottom switched to the top. Which means to find the total area captured between these two curves, you're going to have to set it up as two different intervals. Does that make sense? So this is going to be like area 1, this is area 2. So area 1 would be the integral of the function that is on top is the cosine function, 4 cosine of x, minus the function that defines the bottom part of this region is the 4 sine of x dx. What are my bounds? From 0, and where sine is equal to cosine, 4 cosine of x is equal to 4 sine of x, where sine equals cosine is at the pi 4th angle there. So this will give me my first region. Plus, to get the area 2 part out of this guy, this would be the integral of, what's the top function here is extending that sine. That'll be 4 sine of x plus, top minus bottom, minus the bottom, which is the 4 cosine of x dx. And what are my bounds here? Well, we're picking up at pi 4ths and going until they told us to stop, and they told us to stop at pi. So there's actually two different regions here. I labeled them as A1 and A2, and I'm going to add the two answers for my total area. So here we go. I've got to integrate this guy. Integral of 4 cosine of x. 4 is a constant. And what's the integral of cosine? Sine of x minus 4, holding the constant integral of sine of x is negative cosine of x. This part evaluated from 0 to pi, force. Of course, I would clean this guy up. This would be 4 sine of x. A minus a negative makes it a plus. Negative 4 times a negative cosine of x is plus 4 cosine of x. Evaluated from 0 to pi force. Plug in top minus plug in bottom. 4 sine of pi force plus 4 cosine of pi force minus 4 sine of 0 plus 4 cosine of 0. Plug in top minus plug in bottom. And so on this particular part, what do we end up getting? Well, 4, what is the sine of pi force? Things you're supposed to know from high school. What's the sine of pi force? Square root of 2 over 2. Very good. Plus 4 cosine of pi force is square root of 2 over 2. Minus 4, the sine of 0 is 0, plus 4, the cosine of 0 is 1. So cleaning this guy up, 2 goes into 4 2 times. This will be 2 square root of 2 plus 2 square root of 2 minus 4. 2 square root of 2 plus 2 square root of 2 is 4 square root of 2 minus 4. Put a little parentheses around that. That is the area of that first region. And then we're going to add that to the second integral here. But luckily, it's the same function except the top and bottom is switched. So 4 is a constant. The integral of sine of x is negative cosine of x. Minus 4, the integral of cosine of x is sine of x, evaluated from pi force to pi. According to the fundamental theorems, you plug in top minus plug in bottom. This would be equal to 4 cosine of pi minus 4 sine of pi minus negative 4 cosine of pi force minus 4 sine of pi force. Squeezed it in there. So this would be equal to negative 4. What's the cosine of pi? Pi is 180 degrees over there on the left side of your unit circle, and the cosine of that would be negative 1. Minus 4, the sine of pi is on the x-axis, so y is 0. Minus negative 4 cosine of pi force is square root of 2 over 2. Minus 4 sine of pi force is also square root of 2 over 2. So remember, we're going to add these answers together. So I'm cleaning up this part over here. A negative 4, so negative 4 times a negative 1 is a 4. Minus 4 times 0 is 0. Minus 2 goes into negative 4, negative 2 times, so we get negative 2 square root of 2. 2 goes in negative 4, negative 2 times square root of 2. So I'm left with 4 minus negative square root of 2 minus square root of 2 is minus 4 square root of 2. A minus makes it plus, so this becomes plus 4 plus 4 square root of 2. Cleaning up this part. Now to get my total area, what do I have to do? My total area would be 4 square roots of 2 minus 4 plus 4 plus 4 square roots of 2. The minus 4 plus 4 cancels, adding these two areas together. And 4 square roots of 2 plus 4 square roots of 2 is 8 square roots of 2 units squared. That is the area that is captured between these two curves, representing the two shaded regions right here. It is 8 square roots of 2. Does that make sense? But notice what I had to do to this problem. I identified my region, and I noticed that my top and my bottom switched positions. So when that happens, you have to break off one certain area and then set up a different integral. Because remember, area is top minus bottom dx, or it's right minus left dy. And when your tops and bottoms switch up, you're going to have to break it up into multiple integrals. So what about this guy? Sketch and find the area enclosed by the graphs of f of x equals the square root of x, g of x is equal to 2 minus x, and h of x is equal to 2. Well, this one, I've got 3 different regions on this one, so since I got 3 different regions, I'm going to go for the old handy-dandy calculator here. I'm going to graph all these guys. So I was given f of x equals the square root of x, g of x is 2 minus x, and h of x is 2. So I'm graphing 3 different functions. And I'm going to do a zoom 6, negative 10 by 10, negative 10 by 10 screen. Now, where is it that all these functions, this is the hard part, where is all these functions actually connected at that they've actually captured a certain amount of area? Well, let me go zoom in on this thing a little bit. So I'm going to take my little zoom. I'm going to zoom in, and I'm going to move my cursor right there. That's where all these functions seem to be overlapping at. So I'm going to blow that up. So there's the square root of x graph. There's the 2 minus x graph. Here is the 2 graph. That is my region captured by all 3 of these functions. That's what you got to identify. Where's the region captured when you got more than one equation? Where's the region captured by? So I'm going to kind of draw that on here. So I have y equals 2 was right here. I have the square root of x graph. Starts here and kind of bowls over, so it looks like this. So this is y equals the square root of x graph. And the other one is 2 minus x graph, like this guy right here. This is y equals 2 minus x. And we're talking about this region here. Does that make sense? Now, there's 2 different ways of doing this problem. This is what I want you guys to focus on once you have identified the region. If I do top minus bottom, because these functions are in terms of x, dx means my function's in terms of x, which is what I got here. But if I do top minus bottom, here's my problem. I've got one top part of this region, but I got 2 different bottoms. I got this bottom right here, and I got this bottom right here. So I would actually have to divide this right down the middle and basically do 2 different areas, like I did in the last problem. Does that make sense? And you can do that, but that's twice as much work as I want to do. I only want to do one integral. Because you should always pay attention. Granted, I see top minus bottom because it's dx, but you have the ability to manipulate these equations. Look at your region. You have one top and 2 different bottoms. But if you look at it from a right-left perspective, I have one function on the right, and I got one function that defines the left part of this region. So keep that in mind when you're doing these problems. Don't just look always at top minus bottom because that's what we've been programmed. In certain ways we have because we like dx's in our world. But always keep in mind right minus left. So to save myself some time, I would like to do right minus left. But if I do area as right minus left, that would be dy from C to D. I actually have to convert these equations into y. But I only have to worry about 2 of them. This was my parabola right here. This equation was y equals the square root of x. To solve for this guy in terms of x, this would also mean that x is equal to y squared. I square both sides. And this equation right here was the line y equals 2 minus x. If I solve this thing for x, subtract 2 from both sides, so I get y minus 2 equals negative x. Multiplied by negative 1 on both sides, I would get negative y plus 2 is equal to x, or better yet, x is equal to 2 minus y. These are my equations. I still have to have my points of intersection, but that top part of my region right here was the line y equals 2. So I know this is bounded by 2. So I've got that one. All I need is this point of intersection right here. And this point of intersection is where these two equations equal each other. So 2 minus y would be equal to y squared. Being a quadratic, I'm going to set it equal to 0. Subtract 2, add y. I get 0 equals y squared plus y minus 2. That factors nicely into y plus 2 times y minus 1. Think about it. Set each factor equal to 0. So y plus 2 is equal to 0, and y minus 1 equals 0. Means y equals negative 2, and y equals 1. Now these are my bounds. So I set up my integral. So this was, it's over here at negative 2, but I don't care about negative 2. That's off my screen. Y equals 1 is where this graph is at. So y equals 1 is actually the only point I care about. Y equals negative 2 is down here, and if that parabola continued and curved back over, we would have intersected maybe over down this line going down another place. But that's not my region. That's not, I only care about what's in the first quadrant up here. So, as this being the x-axis and this being the y-axis. So, setting up my area is going to be the integral of right minus left. The right function is the parabola, which is the y squared, minus the left is the line 2 minus y. Again, I cannot stress the importance of the parentheses. Right function, parentheses, minus left function. Because that negative is going to distribute. And if you don't put the parentheses there, you'll forget to distribute and you'll get the problem wrong and the bridge doesn't make it to the other side of the river and people died. It's all your fault. Careless error kills. So, be careful. What are my bounds? From 1 to 2. These are y numbers, 1 to 2, because this is dy. So now I'm going to clean this guy up. So area equals the integral of y squared, and this negative is going to distribute. Becomes y squared minus 2 plus y dy. Evaluated from, integral from 1 to 2 of y squared minus 2 plus y dy. Now I'm going to integrate this guy. Integral of y squared is y cubed over 3, minus integral of 2 is, with respect to y, is 2y, plus the integral of y is y squared over 2, evaluated from 1 to 2. And then I do the fundamental theorem of calculus stuff here. So my area is equal to plug in top. That'll be 2 cubed over 3 minus 2 times 2 plus 2 squared over 2. Plug in top minus plug in bottom. 1 cubed over 3 plus 2 times 1, I'm sorry, minus 2 times 1 plus 1 squared over 2. So 2 cubed is 8 thirds minus 4 plus 2 squared is 4 divided by 2 is 2 minus 1 cubed is 1 third minus 2 times 1 is 2 plus 1 squared is 1 half. So cleaning this up, you end up getting 11/6 when you add them together. You can go common denominator if you want to, or at this point put it in your calculator. But it will be 11/6 what? Units squared. That's how much area is there. Does that make sense? Did I lose you guys anywhere? It's not difficult, but pay attention. And trust me, this was a much better way of doing the problem and instead of doing it by 2 integrals. If I broke it up and integrated from 0 to whatever point this guy is right here, I would have to find that point of intersection. And then top minus bottom. And then add that to the integral of 2 minus the square root of x here from this point to this point over here. I would get the exact same answer, but I would have to do twice as much work because I had to do 2 different intervals. That's why I kind of wanted to pay attention to this problem. Sometimes doing the dy is better than doing the dx. Here's an example of that. Does that make sense? Remember, top minus bottom dx, right minus left dy. So let's take a look at some of these WebWork problems here. This WebWork problem, first one, is, like I said, right off of WebWork. And we throw this one on your notes because a lot of people have screwed it up before. All right, so here's the deal. The width in meters of kidney-shaped swimming pool is measured in 2-meter intervals They are 0, 3.5, 5.5, 5.6, 7.2, 6.5, and 0. Use Simpson's rule to estimate the area of the pool. Okay? Let's see, the area, so we got a kidney-shaped swimming pool. So last time I was in biology class, my kidneys look something like this. The famous kidney-shaped swimming pool, right? So there it is. So now, understand what's going on here. So we first start out here, we start measuring. At this point, it is 0, okay? And we start measuring at 0, and the width is 0. So this would be 0, 0. And then I moved over a 2-meter interval. So I moved over 2 meters, and then I measured it again. So I moved over 2 meters, and I measured again, and then this distance was how much? 3.5. Okay? Then I moved over another. So here was 2 meters there. I move over another 2 meters. Here's another 2 meters, and I measured it again. How far is this guy? This one is 5.5. But this started at 0, so this would have been at 2. This would have been marked at 4. We went to 5.5. I moved over another 2 meters. Another 2 meters, and I measured again. I get 5.6. So 2 meters, 2, 2, 2, that's 6. It's up to 5.6. So I move over another 2 meters. So this is 2, 4, 6. Move over another 2 meters. This is at 8. And I measured it at the 8-meter mark here, and I got 7.2. So at 8, you got 7.2. I moved over another 2 meters, and it's at 10, and I measured it right here. And when I measured it, I got 6.5. So at the mark of 10, again, this is 2 meters and 2 meters, 10, I got 6.5. And then I moved over another 2 meters. So this would be officially 12, and I'm back to 0 again. 12, and I'm back to 0, and we put way more blocks than you actually needed for this job up here. So I had to fill out the chart. Now, what you should realize is this. I want the best estimate for this guy. How many partitions do I have? 1, 2, 3, 4, 5, 6. There are 6 partitions. And because there are 6 partitions, and 6 being even, what is the best way of estimating the area of this side? Simpson's rule, because you can only use even partitions to use it, but Simpson's always gives you your best estimate. So you use Simpson's rule. This would be Simpson's rule for 6 partitions here. What's my formula? Delta x divided by 3 times f of a plus 4 times f of x1 plus 2 times f of x2 plus plus 4 times f of xn minus 1 plus f of b. Remembering our formula. So my delta x in this problem was what? What was delta x? I moved over consistently how many meters each time I took a measurement? 2. Between 0 and 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12. I'm moving over in increments of 2. So my delta x is 2. So this would be 2 over 3 times f of your A point, your starting point is at 0, plus 4 times f of your first internal point was 3.5, plus 2 times your next internal point, which would have been 5.5, plus 4 times your next internal point, which is 5.6, plus 2 times your next internal point, which was 7.2, plus 4 times your next internal point, which is your last internal point, which is 6.5, plus f of b, you end at 12, which was 0. I'm using Simpson's rule. And evaluating these points, what I'm interested in are my measurements here. So this is equal to 2/3 times, and I'll just stick this part on my calculator here. 0 plus 4 times 3.5 plus 2 times 5.5 plus 4 times 5.6 plus 2 times 7.2 plus 4 times 6.5 plus 0. And I get 87.8. And then your delta x was 2 divided by 3. So times 2 divided by 3 is, and I end up getting 58.533333. And because I made this into a physics problem type of thing here, what would my units be? This thing was measured in meters, so this would be meters squared. Very good. So my pool has an estimated area of 58.53 meters squared. So kind of a nice size pool. Does that make sense? All right, more WebWork problems for you guys in this particular section. Take a look at this one. And there's a trick to this stuff, and I want you to start talking to you guys because you guys are science majors, STEM, engineering, math, science, technology, you name it. Here is STEM majors. Pay attention to symmetry, because symmetry can help you save a problem, save a lot of work, and make a little bit of work and be able to analyze the situation. So this trick I'm going to show you guys is based upon symmetry. Here it is. Find the value of C, which is greater than 0, such that the area of the region enclosed by the parabolas y equals x squared minus c squared and y equals c squared minus x squared is 260. And I tried to draw this thing out for you guys. So here's your y-axis, here's your x-axis. We got two parabolas. Which one's which? Well, I got two parabolas. Now, c is a constant. Remember that. C constant. So y equals x squared minus c squared and y equals c squared minus x squared. Well, this x squared is positive, and a positive x squared graph looks like what? U-shaped looking one. So this guy right here must be the equation y equals x squared minus c squared. The other equation is y equals c squared minus x squared. Minus x squared, the negative in front of the x squared, flip the x squared graph upside down. So this is the equation of y equals c squared minus x squared. Where do they intersect at? What are these 2 points right here? Where is this equation equal to this equation? And what value of c makes it such? Look at it. You've got x squared minus c squared, and it's got to be equal to c squared minus x squared. And they both meet up on the x-axis. You know what value they meet up at? At c and at negative c. These are actually the points of intersection. Because think about it. C squared minus c squared is 0, and c squared minus making that xc, c squared minus c squared is 0. So this is where they both intersect the x-axis, and they actually intersect each other at. Okay? And so this area right in here is 260. But I'm going to make this easy for you guys. Well, our goal here is to find C. On this WebWork problem, fill in the blank. C equals what? So that's your job. Find C. This area inside this region is 260 squared units, whatever that happens to be. That's in here. Does that make sense? But if I want to find C, because of symmetry, look at this region right here. I'm going to darken this region so you can see it. This is the point of 0 right there. This is C. How much area would be here? What would that area be? Well, what did I do to this region? Because of symmetry, all these blocks are the same, right? So what is it? It's 260 divided by 4, because there's 4 equal blocks as this thing, we subdivide this guy. I'm using symmetry on this guy. Now that's going to make my problem much nicer. Now 260 divided by 4 is 65. That region right there is 65. And there, to find this region, you find the area of that region, I'll call him area 1 right there, is going to be the integral of the top function, which is the c squared minus x squared, minus the bottom region, but the bottom is the x-axis, which is y equals 0 dx from 0 to c. Now, if you watch some of the other professors teach this class, they're just going to they're going to take this top equation, which is the c squared minus x squared, minus the bottom equation, x squared minus c squared. It'll end up doubling the thing up there. And you're going to integrate from negative c to c, and you're going to set it equal to 260, and you're going to solve c that way. And you can do it, and you'll get the exact same answer, but I'm going to have c's floating all over the place. Now, I've limited the number of c's I got. Still got quite a few of them here, but quite a few less than what I would have done the other way. So cleaning this guy up, area equals 0 to c of c squared minus x squared dx, but we know that's equal to 65. Now let's integrate this guy. Who's c? Well, that's the goal. We've got to find this. But c is a constant. What's the integral of c squared with respect to x? What's the integral of a constant with respect to x? It's the constant times x. Integrate a constant, you get a constant times x. I know it's squared, don't care. C represents constant. So when you integrate a constant, it's a constant times x. Integral of 5 dx is 5x, right? Integral of a constant squared, being it's still a constant, dx is going to be a constant times x. Again, where most people screw this up, I ask them, what's the integral of c squared? They're going to tell me c cubed over 3, because they've been programmed to integrate, add 1 over add 1. But no, c is a constant. It's not a variable. Now, minus what's the integral of x squared with respect to x. That's your x cubed over 3, evaluated from 0 to c. And remember, that's equal to 65. Plug in top minus plug in bottom, made it much nicer. So c squared times c minus c cubed over 3, plug in top, minus plug in bottom for x, you get a bunch of zeros, is equal to 65. So here we go. C squared times c is c cubed minus 1/3 c cubed equals 65. Remember, this is WebWork, so don't bank on the answer being real nice here. What is 1c cubed minus 1/3 of a c cubed? 2/3 of a c cubed. 2/3 c cubed equals 65. I'm going to multiply by 3/2 on both sides. So I just end up canceling here, and I get c cubed equals 65 times 3/2, which is equal to 97.5. I warned you about that. So crappy decimals, because I copied this one right off of WebWork, so crappy decimals here. So c cubed is equal to 97.5. That's where I got the 65 times 3/2 from. Now, what kills off that cube? Take the cube root of both sides. And c is supposed to be greater than 0, so notice I'm using the positive c here, so the cube root cancel. So c is equal to, the answer is the cube root of 97.5. And if you stick that on your calculator, you get 4.602582,041. Welcome to WebWork. There you go. There's your answer. Everybody has a problem in here just like this. You know what the difference between the 150 problems I have for my class here? All they did was change the area. Mine was 260. Your area they'll give you with a different number, but this is the process of what you got to do it. Does that make sense? Don't lose you guys anywhere. The last one on this section is this problem here. All right, and again, look for tricks in symmetry. That's what you look for. It says this: find a number b such that the line y equals b divides the curves y equals x squared and y equals 25 into two regions with equal areas. So again, I drew a picture for you. Here's your y-axis. Here's your x-axis. Here is your parabola. Y equals x squared. Y equals 25 is on top. This is the line, y equals 25. You're supposed to find this line, y equals b, and our job is to find b. We've got to find where the line, y equals b, takes this region and makes it equal to this region, splits it in half. Does that make sense? Now, here's what you should notice. In terms of this problem, okay, I want to do equal areas. These two areas up here are equal to this area, but if these two regions are equal to this region, wouldn't that be the same thing as this region over here being equal to this region? So I'm just focusing on this side of the graph. Does that make sense? But here's your problem. You got y equals b right here. Here's the trick. Y equals b splits down the middle. But I don't have distinct top bottoms. This is the top, 25, and this is the bottom, b, over here. But then, at this little region over here, I got y equals 25, and then here comes my y equals x squared. They got two different bottoms. I got one top and two different bottoms. Does that make sense? I don't like two different bottoms to a top. But instead of looking at it from a top-bottom perspective, look at it from a right-left perspective. When you look at it from a right-left perspective, I've got a single right, single left, single right, single left. And they also gave me the y coordinates. What was this y coordinate up here? It was 25. This one was B. This is 0 because it's the the point of intersection. So this equation, y equals x squared, I'm going to solve for x in terms of y. I'm going to take the square root of both sides, and I get x is equal to the square root of y. This is the graph of x equals the square root of y. That's my right, and on my left, I've got x equals 0 because it's the y-axis. So these two regions, top minus bottom, I'll call this area 1 and this area 2. Area 1 is going to be equal to the integral of right, which is the square root of y, minus left, which is 0, dy from b to 25. Area 2, this one down here, is going to be the integral from 0 to b of the same thing, the square root of y minus 0, right minus left, dy. And so these two guys have to be equal to each other, so you solve this thing. So this is the integral from b to 25 of y to the 1/2 dy. This is going to be equal to, let's see here, integrate y to the 1/2, add 1 over add 1, that'll be y to the 3/2 over 3/2, evaluated from from b, so it'd be b to 25. Fundamental theorem, plug in top minus plug in bottom, but I'll clean them up first. This is 2/3 y to the 3/2 evaluated from b to 25. So this is 2/3 25 to the 3/2 power minus 2/3 times b to the 3/2 power. Okay? What's the square root of 25? 5 cubed is 125 times 2 is 250 over 3. Does that make sense? All right. Minus 2/3 b to the 3/2. But that's going to have to be equal to this area 2 up here. Area 2, integral, this is the integral from 0 to b of y to the 1/2 dy. This will be 2/3 y to the 3/2 evaluated from 0 to b. Plug in top minus plug in bottom. This will be 2/3 b to the 3/2 minus plug in 0. You pretty much get 0 there. So this is equal to 2/3 b to the 3/2. So this is 2/3 b to the 3/2. Your job now is to solve for b. When I add 2/3 b to the 3/2 on both sides, what is 2/3 plus 2/3? 2/3 plus 2/3 is how much? 4/3 b to the 3/2. Now it's algebra. Multiply by 3/4 on both sides. The 3's cancel. So I'm left with 250 over 4 is equal to b to the 3/2. 250 divided by 4 is 62.5. This is WebWork. B to the 3/2. And what kills off a 3/2 power? Raising him to the 2/3 power. So B is going to have to be equal to 62.5 to the 2/3 power, which is honestly crappy number. Sorry, it is what it is. Parentheses 62.5 raised to the 2/3 power, and you get the answer of 15.749013112. That is the answer of what B has to be. Does that make sense? Beautiful algebra, but the idea of symmetry is very important in this section. I can't iterate that enough. Study hard, and I'll see you guys on Friday, where we'll start section 7.2. See you guys then.